Welcome to UV Physics. So I request you please watch the first video, first class video before going to watch the second or third lectures. Because here we are introducing a new method to solve any type of a quantum circuit, 2 qubit, 3 qubit, any circuit you can solve. So here we are introducing a decimal notation to represent the qubit states. uh, it's a new method and a new approach. So I request you first watch the lecture number 1 before watching the other lectures, and let us continue the second lecture now. Welcome back. And in the first lecture we have discussed about this single qubit quantum gates, and we have explained a few examples of quantum circuits. I hope you understand that method, and this 2 qubit quantum gates is really interesting. Let us start. So whenever you have 2 qubit quantum gates, and this is represented by this CU, C for control, and U. This U stands for this a single qubit quantum gate. That means unitary operator corresponding to a single qubit quantum gate. Now we can represent like this. We have 2 qubits. This is the control and this is the target. Okay, and here we have this unitary operation, just I'm taking it as 1, and I have already discussed the decimal notation. Since we have 2 qubits, the decimal notation will give you here 1 and here 2. Observe carefully, this is really interesting. Generally what we will discuss in this 2 qubits, here we have a control bit. It is having two options. Maybe it is in off state or it is in on state. For example, if I take a C equal to 0, that means off, or C equal to 1, it will be in on state. If C is in off state, what about the final state? The final state is nothing but there is no change, that is a CT only. If a control bit is on, that means the final state is nothing but C, and this operation U operates on that target if the control is on, means UT. This you know already, I hope. Now what I'm explaining in this new technique. So earlier we have written a single qubit quantum gate operation as U of 0 comma whatever the target. It is 1, 2, 3, anything you can take it as, you can take that target. But here the operation, this is very crucial. The operation is represented by, and let me write this U matrix also. This U matrix I am taking it as A, B, C, D. Generally anything you can take. But same thing, no change. First column you have to use whenever target is off. Second column how to use whenever target is on. No change. Okay, right. Now the operation is represented by, this is a U of, it may be X, it may be head mod, it may be Z, or it may be S, anything. So U of, see carefully, earlier we have taken 0, now it is a C. C for control. Remember, you have to take the decimal value of that control in my method. Don't forget this. So C comma C plus T. That's it. So what is this? I didn't understand. Yeah, let me explain. Now in this present example, if I take like this is CU control operation. This is a control and this is target. I have decimal notation, I told you 1 and 2. Okay, as per this is a U of, here what is the control? 2. That's why 2 comma C plus T. C is 2 and T is 1. C plus 2. Sorry, C plus T. That is 2 plus 1 is nothing but 3. Okay, this will create a superposition of a 2 and a 3. It depends upon the type of that unitary matrix. Okay, type 1, type 2, type 3, anything. Okay, more general one is type 1 only. Okay, right. So that means what? For example, if you have 2, 3, Just I'm taking combinedly like this. And what this circuit will do, this total circuit actually. Okay, so we have already taken U as a ABCD, this unitary matrix. Okay, so 2 is in yeah, the same thing, same technique, whatever I have explained. This 2 is off and 3 is on. That's why it will take A2 plus B3. Since 3 is in on state, you have to take the second column, C2 plus D3. That's it. Now, what about the other two states, that is 0 and 1? No change. Okay, because 0, 1 not came here. That's why 0, 1, the circuit won't do anything. Now, let me take example, then you will understand. Okay, so let us start with this C naught. The first one, I'm taking this C naught gate. Okay, so here we have two qubits. This is a control and this is X. This is a CX. We have two qubits in our notation. We have to take it as 1 and 2. Now see, so simple, very easy, very easy. Now here U is nothing but X. X, that is a type 2, it will flip. So here the control is 2 and the target is 1. Just now I said C comma C plus T, that is nothing but X of 2 comma 2 plus 1 3. Just take the control and come to the target, add 2 plus 1 3. So that means if you have 2 3, it will, this 2 3 circuit will make it as 3 2. And what about 0 1? No change, no change in this 0 1. Let me take one more example. So I'm taking a CH, control H. Okay, so this is 1 and 2. Okay, so our unitary operator is a H here. It's very simple. First come to the target, sorry, first come to the control. Control is 2 comma, come to the target, that is a 1, 2 plus 1 3. So it creates only superposition of 2 and 3. It won't change that 0 and 1. So 2 is off, 3 is on. That means 2 3, 2 3, 2 off. That's why 2 plus 3, 3 on, 2 minus 3. If you practice that first lecture, you can write very easily. Of course, normalization constant will be there, that is 1 over root. If you want to write properly, you can write this as 1 over root 2 ket 2 plus ket 3, and this is ket 2 minus ket 3. And what about 0 and 1? No change, no change in 0 and 1. Let us take one more, that is here I am taking this time control Z I am taking 1 and 2. This is a Z, no need to write CZ, just Z only, because operation depends on that operator Z only. Control is 2, 2, 2, 1, 2, 2, 1. Just say like this, 2, 2, 1. From where it is coming? 2 and it coming to 1. 2, 2, 1. That is 2 comma 3. So this is 2 off and 3 on. And you know what is the Z operator? 1, 1, sorry, 1, 0, 0 minus 1. Off and on. So Z won't flip anything. It will give the same state with the phase changes. That's it. That means 2, 3. The first column 1, that's why 2 only. Second column you have minus 1, that is minus 3. Clear? And 0 1. So this is a no change 0 1. And next fourth one, I am taking this as let me take a T gate, control T. So here it is again 1 2, and you have to write a T from where to where? 2 to 1. That's why 2 comma 3. 2 is off, 3 is on, and T operator 1 0 0 e power I pi by 4. First column off, second column on. That is 2 3, 2 is off, no change, 3 on, that's why phase change, e raised to I pi by 4 3, and there is no change in the 0 1. Okay, and if you want, I will take few more examples. That is, here I am taking control s. Okay, 1 2. So just take s from where to where, 2 to 1, that's why 2 comma 3. Off and on, S matrix 1 0 0 I. So this is off and on. 2 3, the circuit what it will do, 2 off, because we have first column 1 0, that's why 2 only, and 3, there is a phase change I 3. I means here the phase change is pi by 2. Okay, so because e raised to I pi by 2 equal to I, right? Okay, and take another example also. Here I have Rx, and again I'm taking a 1 2, and the operation Rx of from where to where, 2 comma 3, you have to add that a target to the control, 2 starting comma, add that a target bit to the see decimal addition only, no binary, it's a normal decimal addition only. Okay, right. So Rx operator, let me write, maybe you forgot, cos theta by 2 minus I sin theta by 2, and minus I sin theta by 2 cos theta by 2. So if you practice like this, definitely it will be very easy. And here we have 2 3. So what it will do, this 2 is off, that's why cos theta by 2 2, minus I sin theta by 2 3, and 3 is in on state, that is a minus I sin theta by 2 2 plus cos theta by 2 3. Like this you can proceed. Any examples? And I request you please try this last one yourself, that is 1 2 we have here. Sorry, I will give this, you have to remember. And this is ry of theta. So fine for this. Okay, right. Okay, so here we have seen this control U operations, that is a 2 qubit quantum gates. Now sometimes that control and the target bits will be interchanged. Then how to proceed with this new technique? Okay, so let me take that. Sometimes control and T qubits are interchanged. Then how to do this? Okay, so here I'm taking the, so earlier the first one is control and the next one is a target. Now I'm taking a reverse like this. So no problem. Now this is a control and this is a target. Remember, we are using the decimal notation, that is here 1 and here 2. So always you have to go from control to target, control bit to target, use that decimal states addition. Okay, so now this is a I'm taking the U operator as a B C D, and this one is as usual, first column for off, second column for on, and this operation can be written as U off. Now where is the starting one, control 1 comma, you are going to 2, that is 1 plus 2 3, that's it. So it creates a superposition of 1 and 3, and what about 0 2, it won't do anything, that's it. So 1 3 and the circuit. Here 1 is off, 3 is on, that's why A1 plus B3 first column, and 3 is on, that's why second column, C1 and D3. You should not write C3 and D1, please remember order, that 1 3 order must be always the same. Let us take some examples. First one I'm taking this reverse C naught gate. Okay, so as per our notation, this is 1 comma 1 2, and this is x, from where we are starting from 1 to 1 plus 2, that is 3. So it will flip 1 and 3 only. 1 3 will become, because x is having that flip operation, that is a 3 1. And what about 0 2? No change. Sorry. And let us take the second. Here you have a reverse control jet, that means a target and control bits are interchanged. Here 1 and 2, so same thing, starting from 1 going to 2, 1 plus 2, that is a 3. And you know this is off and this is on. Okay, you know jet operation already. Off state means no change, on state means add the phase of that pi, that is -1 will be added. So here it is 1 3, 1 no change because it is off, 3 this is a -3. And what about 0 2? No change. Wait a minute, somewhere we have this same answer, 1 to 1, 0 to 0, 2 to 2, but 3 become -3. Somewhere we have seen this. Wait a minute. Yeah, here. See here, 0 and 1, no change. 2 also no change. And 3 change to -3. So that means we can conclude like this. Whenever, if you have a control jet gate, okay, if a control and a target qubits are interchanged, there is no change in the CZ operation. That means, if C and T are interchanged, so no change in CZ control Z operation. So we can represent like this. This is control and this is target. Here we have this CZ gate. This is equivalent to uh, control and targets are interchanged. So here this time this is control and this is target, and both are same. Okay, so I hope you understand this, and still if you want some more examples, I will take this one. So here I have ry of theta I have taken, and this one. Okay, so here 1 and 2, so this is ry of, from where we are starting, from 1 where we are going to 1 plus 2 3. So this is off and this is on. Please write Rx of theta operator, sorry, Ry, I'm sorry, Ry. So this is a cos theta by 2 minus a sin theta by 2, and this is a sin theta by 2 and a cos theta by 2. As usual, first column is off, second column is on. So here let me take 1 3, and what this circuit will do, this 1 is in off, that's why you have to take the first column, cos theta by 2 1, plus a sin theta by 2 3. And next 3 is in on state, that's why you have to take the second column, minus a sin theta by 2 1 plus cos theta by 2 3. And what about 0 and 2? It won't change. Like this. Okay. Okay. Now let us extend this to some other thing. You can take one more example if you want. I will end this. Or you please try. Rz of theta. I request you please try this. And if you don't know this Rz of theta, let me write. This is e raised to minus I theta by 2, 0, 0, e raised to I theta by 2. Okay. So remember, uh, whatever this control and target interchange or not interchange does not matter. First always come start with the control. So start with the control bit and going towards the target, that means u of c comma c plus t. First to take the control and next add control and target. Decimal notation, decimal addition only, no binary addition. Okay, so you please try and check. Okay, next let us take a very interesting one, combination of quantum gates. Now here I am taking some combination of quantum gates. So till now we have discussed the single qubit quantum gates and two qubit quantum gates. Let us combine both, then how it will be. Okay, but remember a few points while we are doing this a combination of quantum gates. Remember, uh, generally the order is top to bottom. Okay, so because here control bits, co- control unitary operation is there, that means control cu gate is there, that is 2 qubit gate. That's why my advice now, please take from top to bottom. If you have single qubits you can take order, it's not a problem, but in the middle if you have any c naught gate or cu gate, then little bit careful. So that's why finally we'll conclude this point here like this. Always take the order from top to bottom, and the next left to right. See, maybe you heard this, whenever you are multiplying you have taken right to left, maybe somewhere you read this also, whenever you are writing the matrices you have written from right to left. The reason is, see, this is the initial state and here you have one operator, here you have one operator. If you write from right matrix to left matrix, then only this left side matrix will operate on this first. That is the reason. But remember here I'm taking operations first. So that's why I will go from left to right. So don't get confusion. Okay, I'm talking about operations, not matrices. Okay, so take the operations from left to right. No confusion, don't worry. Left to right. Sometimes I used to multiply the matrices, because otherwise if I write all the operators it become it's a huge operations, I mean so many operations will come. So then what I will do, I will multiply a few matrices. But whenever you are multiplying the matrices you have to multiply from right to left only. This one don't forget please. Okay, matrix multiplication always from, this is a general, everybody used to say this only, right to left. So don't forget these are 3 points. Now let me take one small example, then I will discuss. First one, here I have two qubits. It's a very nice, very interesting one. Please listen carefully. Here this is a 1 and a 2. I'm taking a H gate here and a C naught here. Then how to solve this? Okay. Now here we have two quantum gates. One is H, another is a C naught. You can start with H. I told you we have to go from operations, go from left to right only. Always write the operations from left to right. But whenever, in case if you are multiplying any operations, multiply from right to left. Because we will multiply as matrices. We can't multiply the operations directly. We'll multiply them as matrices. Okay, please remember this. Now I'm going from left to right only. So this is the first one H. See, this is on 2. This is a single one. It's a single quantum bit. That's why 0 comma target is 2. Now what's the remaining? 1 is remaining. That's why add 1 comma 3. Next one, 2 qubit quantum gate. That is a C naught. Okay, that is X. where you are starting 2, that is 2, and you are coming to 1, that is a 2 plus 1 3. That's it. It won't do any other operation. Now I told you earlier, if you have a head mod operator, please take the first column and remember always off on off on off on. Okay, right. So I'm taking this 0 and 1, first a head mod. So 0 is off, that's why 0 plus 2. I hope now you understand. 1, it is also off, it creates a superposition 1 plus 3. Okay, why you have taken plus plus? Because the first column is 1 1. Next you have to operate X operator because you are coming from left to right, and it won't do anything this is with the 0, but 2 will be changed to 3, 1 no change, and 3 will become 2. I hope now you understand this is entangled state. Okay, so here it is a 1 by root 2. If you want, you can write that 0 0 become 0 0 plus 1 1. Okay, and 1 become, that means 0 1 become 0 1 plus 1 0. If you want, you can write in the binary notation and check whether this is right or wrong. And the next one is a 2 3. You need not to do anything, I told you already. Whatever the earlier final answer you have, this is only for H, not for other other things. Okay, whenever head mod is there, do like this, otherwise proceed with the original method, that is 1 over root 2. Here 2 is on, that's why 0 minus 2. 3 is on, that's why 1 minus 3. Next X. So here 0 no change, 2 will become 3, 1 no change, 3 will become 2. That's it. Okay, so let us take one more example. Okay, so here I'm taking a second example. Let us change the order. Here first I am taking a C naught and here it is a H. Two qubits are there, 1 and 2. I told you how to come from left to right. So that's why X first, starting from 2, coming to 1, that's why 2 comma 3. Strike a line, each operation strike a line. Then H, it is on 2, that's why 0 comma 2. Now add 1, H of 1 comma 3. Now here anything you can take, it's not a problem. I'm taking all the things together, no need to get tension. 0 1 2 3 I have taken. So here a 0 no change, let me take another color. X is operating now, 0 no change, 1 no change, 2 will become 3, 3 will become 2. Okay, next come to this. This is off on. 0 is off, it creates a superposition of 0 and 2, that's why 0 plus 2. 1 is off, it creates a superposition 1 plus 3. 3 is on, that's why it creates 1 minus 3. 2 on, 0 minus 2. Okay, only two states are there, normalization constant 1 by root 2. Okay, right, and take one more. So here let me take like this, and I have taken a reverse one, C naught. No problem, anything you can solve by if you understand this technique. Left to right, first head mod is coming 0 comma 1 because it is on 1, and add the another one, that is a 2, 2 comma 3, and X, it is going from 1 because always starting control bit is 1, 1 comma going towards 2, 1 plus 2 3. That's it, right? So whenever head mod is there, it's better to take a 0 to first, otherwise you can take all the things at a time. Let us see, because you already understand. So head mod operation, off on, 0 0 plus 1 1, 0 minus 1 2, 2 plus 3 3, 2 minus 3, and 1 over root 2. Next X operation, that is a 0 plus 3 1 2 3 3 2 1, 0 minus 3 2 plus 1 2 minus 1. like this you can do very easily. Okay, so let us take one more. Now here third one I'm taking, let us take like this is the head mod gate, and here we have control not C not. Now two qubits 1 and 2. Okay, so you have to take from a left to right. First head mod is there, see that is on 2, that's why 0 comma 2, add 1, that is 1 comma 3. Next gate is going from left to right, don't forget this, that is x 2 comma 3. I hope you understand why it is, and strike a line, and h is repeated one more time, you have to write, that is h of 0 comma 2 and h of 1 comma 3. Okay, now let us see 0 1 2, 0 1 2 3, you have, right. So here I have taken all the states at a time. Okay, no problem. So please remember this technique. Oh, sorry. Off, off, on. This X is always flipping the states. That's not a problem. So here this is a 0 off. That's why 0 plus 2. Let me take another color. So 0 plus 2 and 1. It is off, that's why 1 plus 3, because 1 is in the combination of 1 and 3. 2 on, that is a 0 minus 2, 3 on, 1 minus 3. I hope you understand. I will write the normalization constant at the end, it's not a big deal. So this is x, so 2 will become 3, 3 will become 2, that's why 0 plus 3, 1 plus 2, 0 minus 3, 1 minus 2. Now see, again one more head mod operation came. Okay, so here 0 is in off state, so 0 become 0 plus 2. Let me take another color. So how I'm writing for this is 0, 0 plus 2 plus 3, that 3 is in on state, be careful, 1 minus 3, because it is a combination of 1 and 3. Next 1, it is off, 1 plus 3 plus 2, it is on, that's why 0 minus 2. Next 0, 0 plus 2. If you observe carefully, this one 0 3, only middle sign is changed. That's why here just change the middle sign, and second one and last one only middle sign change. That's why 1 plus 3 minus 0 minus 2. That's it. So here 4 states are there, 1 over root 4. Actually 1 by root 2, 1 by root 2, that is 1 over root 4. Okay, so I hope you understand this. Right. So let us go to the next one. Next one is a little bit quite interesting. And here the next I am taking a quantum circuit like this. This is the C naught, and here we have H and H gate, head mod gate. I hope you know this. This is equivalent to control jet, but let us apply our technique. Okay. So this is a 1 and a 2. So first I am taking a left to right operations, that is a h of, listen carefully, this is so interesting, 0 comma 1, and you have to add 2, that's why 2 comma 3. Next control, I mean x, this is the C naught, 2 comma 3, and next head mod again, head mod 0 comma 1 and 2 comma 3. Now listen. Sir, if you are having these many operations like this, how we will do? I'll tell you a small technique. So commutation, interchange, or yeah, AB equal to BA operations like this. This is possible in our technique only when, observe carefully, here there is no 0 comma 1. So that's why this h of 0 comma 1 directly you can write here. That means you are interchanging that first one. Okay, and this h, you cannot multiply h01 with h23. H01 is multiplied with h 0 1 only. Then it is h square 0 comma 1, which is identity 0 comma 1. So this one won't do anything with that 0 and 1 states. And the next one, h2, next one you can apply our technique. So we have 2 3, that means yeah. So the remaining is a h of 2 comma 3 and x 2 comma 3 and h 2 comma 3. If you want, you can apply our technique, you will get the same answer. But you know, all of you, I mean most of you know this h x h is nothing but z. Okay, so that's why I can write this as z of 2 comma 3. Okay, so this will become, okay, this will become z 2 comma 3. Carefully see 2 comma 3. What is the meaning of 2 comma 3? First one is always a control. So that's why this is 1 and a 2, you are here. And how you got this 3? That is a 2 plus 1. So C plus T. So T is a 1. That means the target is 1. Like this. Okay. That's it. That means if you take a 2 3, this is a Z operation. That means a 2 is 2 off, 3 on, 2 minus 3. So finally we can conclude like this. So if you have uh, you have C naught here and a head mod gate and this head mod gate. This is equivalent to this control Z. Okay, right? And you know that if control Z, you can interchange control bit and target bit also you can interchange. Next, let us take a few examples. Um, yeah, so I'm taking this circuit. So here H, and this is a C naught, and here H like this. Let us check what you will. Okay, just now we have seen this this gate. This is nothing but control Z. So now I'm going to replace this with the control Z, and here you have control Z gate, and the rest of the head mod operators, head mod gates are as usual. And earlier we have discussed whenever control Z is there, control and target bits can be interchanged. Then you will get here Z, because here I interchange that control and target bits. Here also you can change this. It's not a trouble. It's not a big deal. But head mod gates are as usual. No change in the head mod gates. And just now we have discussed H Z H is nothing but X. So this is nothing but, again we have H Z H, that is this one, which is nothing but X. So we got a C naught, that means mm, control and target bits of C naught are interchanged. Okay, so we can say it upside down, something like that. Okay, so that's it. And take the another example. Let me take head mod here and on C naught, and again head mod I am taking and a C naught. No need to get tension. So just aram se apply our method. So here 1 and 2, don't forget this. So first left to right, head mod 0 comma 2, add 1 1 comma 3. Next C naught, that is a 2 2 3. Next again head mod 0 comma 2, 1 comma 3. Next again x 2 comma 3. That's it. Now observe carefully. Now you got a doubt. So Shall we multiply this h of 0 comma 2 like this? Earlier you have multiplied, here h of 0 1, h of 0 1 you multiplied. Shall I multiply here? No, because see, h of 0 to h of 0 2, here you should not have either 0 or 2, but you have 2 3, so that's why we should not multiply. Then how to proceed? Then follow the usual method. So here I am taking 0 1. See, first elements I have taken. First head mod 0 plus 2. I hope already you got some perfection, that's why I'm doing fast. So 0 plus 3 and 1 plus 2, and again head mod. So 0 off, 0 plus 2, 1 sorry, 3 on, 3 on, that is 1 minus 3, 1 1 off, that is 1 plus 3, and 2 on, that is a 0 minus. Next again x. Okay, so this will give 0 plus 3 plus 1 minus 2, 1 plus 2 plus 0 minus 3. Now the next one, no need to worry. Next one we can write directly, that is a 2 3. I'm not doing all these things directly, you can write. The reason is 2 is on. Here the combination is a 0 2, 2 is on, that's why 0 minus 2 and 1 minus 3. So no need to do all these things, directly you can write. In the middle you have minus, wherever middle sign is there just change it. 0 plus 3 minus 1 minus 2, 1 plus 2 minus 0 minus 3. That's it. Okay, right. I hope you understand this. So I will give you a few examples. You please try, and if you are facing any trouble, please inform me. And here we have head mod, and this is a C naught, and this head mod. Second one here X gate, and this control head mod. And third one, so here I have head mod gate and another control head mod gate. Okay, so whatever it is, no need to get tension, just go from left to right. And the last one more is left in this 2 qubit quantum gates, that is swap gate. The last one, swap gate. Okay, so swap gate, generally here we will write like this, and we will represent like this, A, B, and here you will get B, and here you will get A. So then how to represent this in our decimal notation? Okay, so here I'm taking this swap gate. So 2 qubits are there, that is a 1 2. Then it's very simple, it's very simple. I'm using this SW, okay, because I cannot take a first letter S because already S gate is there. SW, that is 1 and 2 will interchange, that means 1 comma 2 only. Either you can write a 2 comma 1 or 1 comma 2, it's not a problem. Okay, right. And I will explain, if more number of qubits are there, then how to do all these things in the next video we'll discuss. Okay, let me explain one interesting thing here. I'm taking the combination of C naught gates here, like this, C naught and a reverse C naught and a C naught. Let us find. Now here swap gate 1 2 means what? 1 become 2 and 2 become 3, like this. Just like flipping, but you cannot say it's a flip. Okay, so 1 become 2, 2 become 1. Don't say flip, sorry. So here 1 2, proceed, x of 2 comma 3, because the starting 2 ending 1. So that's it. And the next x is a 1 comma 3, because the starting 1 ending 2. Next x is a 2 comma 3. Okay, now I want to check 1 and 2 only, that's why I'm taking 1 2. If you want to check another You can check, you can take all the things, no problem. 0, 1, 2, 3 I'm taking. So 0, there is no 0 in all these things, that's why 0 is as usual. Next one is 1. See, always go from left to right. Any 1 here? No. Then go to the next. Any 1 here? Yes. 1 become 3. Then go to the next. Any 3 there? Because already 1 become 3. Now you are in the 3 state. So 3 become 2. Still not understanding? One more time. So here we have 1 initial state. So 1. You have to travel from left to right. There is no 1. Go to the second. 1 become 3. Don't write. So come to the end, till the end. Go till the end. Next 3 become 2. Right. Next one 2. So here it is 2. 2 become 3. 3 become 1. And here is no 1. That's why 1. One more time. Here it is 2. 2 become 3. 3 become 1. Here there is no 1. That's why I have written. Next one 3. 3 become 2. Here there is no 2. But don't stop till the end. Again 2 become 3. That's it. Now if you see carefully, this one, 1 2 2 2 2 1, 0 and 3 remains the same. And still not understanding, take one more. So this time I'm taking a reverse C naught, and here C naught, and again a reverse C naught. This is 1 2. So I'm taking here, this is x starting from 1 going to 2. That's why x of 1 comma 3. Next x of 2 comma 3. Next x of again 1 comma 3. Okay, right. Now here I'm taking this 0 1 2 3. I hope you understand, that's why I'm taking directly. So you please check, here is no 0. Go next, no 0, no 0. That's why 0 is as usual, I mean same. Next 1. Here 1 become 3, 3 become 2. Here is no 2, write 2. If there is no state, just immediately write. Next 2. Here is no 2, go to the next. 2 to 3, 3 to 1. Next. And here 3. First one 3 to 3 become 1. Here is no 1. Now 1 become 3. That's it. So same answer. Okay. So we can conclude like, we can conclude this. What means, so if you have a swap gate, this is equivalent to C naught, reverse a C naught, again a C naught, and this is equivalent to uh, like this. Okay, right. So fine, and till now we have discussed about this 2 qubit quantum gates. Okay, so I hope you understand this method and you are following. Okay, so in the next lectures we will discuss some more interesting points. Okay, so thank you, and if you are facing any trouble, so please let me know. And okay, so thank you, we'll meet again. Right. So till now we have discussed how to solve these quantum circuits involving a single qubit gate and a 2 qubit gates. Let us take a few more examples. Now here I am taking the first one, taking 3 states, 3 qubit states, and a single qubit gates I am taking Hadamard, and here it is Pauli X, and this is S. So how to solve this? Generally here the initial state they will give 0 0 like that, but with this method you can solve for any input. Okay, so give the decimal notation to the qubit states starting from LSB 1 2 4. Now write the operations top to bottom, left to right. The first one single qubit, that's why u of 0 comma target. So that is a 0 comma here target is a 4. Next you have to add the remaining states. Now first I am adding 1 to the above states, that is a 1 comma 5. Next you have to add this 2. Remember, whenever you are adding any state, you have to add to all the previous operations. That means h of 2 comma 6 and h of 3 comma 7. And after that we have x. This is x 0 and the target is 2. Next add 1, x of 1 comma 3. Next add 2 to the previous operations, that is sorry, not 2, 4, because x already taken 2 and 4 is remaining, 4 comma 6, and here it is a 5 comma 7. And the next one is s, it is on first one 0 comma 1. Now I am adding 2, that is s of 2 comma 3. Now I am adding a 4 to the previous operations, 4 comma 5 and 6 comma 7. Now I told you already, whenever head mod is there, better to take this first decimal values of that ordered pair. That's better. Okay. So okay, 0, 1, 2, 3 I have taken. Now first head mod operation, just go from left to right. Okay. So head mod operation. So the 0 is off, here off, second on. So a fixed one, I think I have already explained what is the meaning of that off and on, off, on, right. So this is a 0 plus 4, 1 plus 5, 2 plus 6, 3 plus 7. If you are watching this video directly, I request you first watch the first lecture and then come to this video. And next x, which will flip the states, 0 become 2, 4 become 6, 1 become 3, 5 to 7, 2 to 0, 6 to 4, 3 to 1, and 7 to 5. It's very easy. Next we have this s. I hope you remember what is this s operator, 100i. Okay, and the first column is off and second column is on for on state. So here 2 is there, 2 is in off state, that's why no change. 6 is also in off state, no change. So and here we have 3, 3 is in on, like in on state, that's why 3 I3, and 7 is also on, that's why I7, and 0 off, 4 is also off, but 1 is in on state, that's why this is I1, and 5 is also on, I5. So right, finally if you want to write this normalization constant, you can write 1 by root 2, and this is a 1 by root 2. You can write like this. This is a 2 plus 6, and I is a phase factor, and here's 0 plus 4, and I1 plus I5. I told you earlier, whenever head mod operations are there, it's very easy to write the rest of the states. Now the rest of the statements, take the second elements in that order pair, it is 4, it is a 4, 5, 6, 7. Now if I take a head mod operation on this, now whatever earlier we have, that middle sign will be changed, that is a 0 minus 4, 1 minus 5, 2 minus 6, 3 minus 7. And I need not to do all these things, directly you can come to the answer. This is the one advantage if you start with the head mod first numbers of that ordered pair. So it's simply a 2 minus 6, and this is I3, the middle one is minus I7, and this is 0 minus 4 and this is I1 minus I5. That's it. Okay, right? And now let us take some other examples. This time let us take a combination. First I am taking 2 qubit states. Here I have Hadamard, and this one control S, and again Hadamard gate is there, and after that one swap gate. Let us do this. Okay, so no need to get tension, top to bottom and left to right. So first give the decimal notation. This is a 1 and a 2, and here we have Hadamard. It is on 2, that's why a 0 comma 2. Next we have to add the remaining, that is a 1 comma 3. Next here we have S, control S. You need not to write CS, you can write S. So you are coming from 2 to 1, that's why 2 comma 3. Next again Hadamard, it is on sorry, it is on first state, that's why 0 comma 1. Add the remaining, that is H of 2 comma 3. And next swap, just I am taking the letter SW. Okay, this is a swapping between 1 and 2, decimal states 1 and 2, right? Okay, now I told you already, first take these two, 0 1. Once the head mod is operated, it is a 0 plus 2 and a 1 plus 3, and a normalization constant you can write at the end, or now also you can write. And this is off and on. S will add I as amplitude to the on state, and off state remains same because S is 100 I. First column stands for off state and second column is for on state. So I will write the normalization constant at the end. Now 0, there is no 0 actually, 2 no change, 1 no change, and 3 I3. Next again Hadamard operation we got, so no issue. I will write the normalization constant at the end. Now here 0 is there, this is off and on. So this is 0, 0 plus 1, 2, 2 plus 3 here. 1 on state, that's why 0 minus 1 plus I, it is a 3, that is a on 2 minus 3. And finally swap gate, it swap 1 and 2. So the final answer here it is 4 states are there, that's why 1 over root 4. 0, 2, 1 plus 3, and 0 minus 2 because 1 and 2 swap, and plus I 1 minus 3. So once you got this 0 1, you can write directly that other one 2 3. No need to do all these things because the initial operation is head mod. This is possible whenever initial operation is head mod, because here the initial operation is with head mod. The reason is if you write the starting 1, so it becomes 0 minus 2 and 1 minus 3, and rest of the operations are same. That's why what I am saying is finally come to the last step without doing all these things. Just change the sign in the middle. Just change the sign in the middle. 0 plus 2 minus 1 plus 3, 0 minus 2 minus I 1 minus 3. That's it. Okay, right? So let us take one more example. Now here we have 2 qubit states. Give the decimal notation 1 and 2. Now write the operations. So here we have Hadamard, 2 Hadamard gates are there, but no issue. Start from top to bottom and left to right. So the first header mod is 0 comma anything you can take, 0 1 0 2, anything you can take, it's not a problem. So 0 2 I'm taking, and add the first one, that is 1 comma 3. Again you have to take a header mod. The reason is you are coming from top to bottom first, so that's why again h of 0 comma 1. Now this time I'm adding 2 2 comma 3. Next z is there, that is on 2, that's why 0 comma 2, add 1 1 comma 3. And the next x, that is you are going from 1 to 2. Okay, so whenever 2 qubit gate is there, just see the starting number and ending number. So that is control to target. So control is 1, target is 2, that's why 1 plus 2 3. That's it. So off on like this. For x it is not required because it's just to flip the states. Right, now first I am taking 0 1. This is 0, let me take here 0 1. So the head mod operation will do 0 plus 2 1 plus 3. I hope you understand. I'm writing the normalization constant at the end. And after that again head mod operation is there, 0 becomes 0 plus 1. All of you please see this one. Okay, and plus 2 is in off state with a linear combination of 2 and 3, 2 plus 3, and 1 it is in on state, that's why 0 minus 1 plus 3 on state, 2 minus 3. So if you want you can write the normalization constant 1 over root 4. And now z operation, uh, 0 and 1 are in off state and 2 and 3 on state, that's why 1 over root 4. So 0 off state, 1 off. And next, sorry, so 2 is in on and 3 is also on, that's why minus 2 minus 3. So that's why we can write it as minus common, that is 2 plus 3. Next one, 0 minus 1 as usual, no change in the 0 and 1. And after that 2 will be changed and 3 also a phase change will be there, minus 2 plus 3. So just I am taking minus common, then it become 2 plus 3. Sorry, 2 minus 3. This is 2 minus 3. Okay, right, because minus 2 plus 3 minus common 2 minus 3. That's it. And after that we have one more operation, that is x. So it flip 1 and 3 only, 1 2 3 3 2 1. So 0 plus 3 minus 2 plus 1 and 0 minus 3 minus 2 minus 1. That's it. And normalization constant 1 by root 4. So the advantage of this method is you need not to do the operation of the next one, that is a 2 3. You can write it directly, come to the last step, whatever the sign in the middle, just change it. So if you have any confusion, please do this entire process and check whether you are getting the same answer or not. Okay. Right. So thanks for watching, and I request you please watch the lectures in order, first lecture and next second one, and like that. Okay. So thank you. And if you have any trouble and if you are facing any problem while solving the circuits, so please let me know, and definitely I will help you. Thank you.